At the outer rim of the reef, where the turquoise shallows plunge into cobalt depth, an invisible frontier rules the ocean's traffic. This is the shear zone, a shifting corridor where fast oceanic currents crash into the slower, looping eddies of the reef lagoon. Water folds upon itself here, creating slicks of turbulence and ribbons of clarity, a living border between two worlds. For the tiger shark, it is both highway and hunting ground. Each pass along this edge is a patrol through the thin membrane between calm and chaos, a place where physics and instinct converge into one of nature's most elegant ambush systems. To the untrained eye, a tiger shark's movement looks almost lazy. Its broad, blunt head swings gently from side to side, and the long tail beats with unhurried grace. But beneath that composure is precise calculation. The shark's body reads the water the way a hawk reads air pressure. Each eddy, each temperature drop, each scent thread matters. The edge between fast and slow water becomes an information superhighway. Small shifts in salinity, temperature, and current speed mix here, carrying fragments of everything the ocean contains. The drift of fish scales, the faint trace of turtle blood, the musk of a decomposing whale carcass. The tiger shark's nostrils, positioned on the underside of its snout, are not just scent receptors. They are direction finders, capable of detecting concentrations of a single molecule in 1 trillion parts of seawater. When the shark moves along this fluid frontier, it is not simply cruising. It is surfing on hydrodynamic cues invisible to us. The moment the faster offshore current presses against the slower reef flow, a narrow ribbon of pressure difference forms, and the shark slides into it. Here, drag drops, lift increases, and the animal can glide effortlessly for long distances with minimal tail beats. Marine biologists who have tracked tiger sharks with accelerometers notice how their swimming effort plummets when they hug these current seams. Energy saved here is energy invested in survival. In a world where even apex predators live by tight margins, efficiency is everything. The tiger shark's body itself is a masterpiece of edge-riding design. The high dorsal fin acts like a sail, stabilizing it in mixed currents, while the pectoral fins, broad and slightly curved, generate subtle lift. By angling them just a few degrees, the shark can bank left or right without losing altitude in the water column. It is a kind of underwater glider, balancing the competing forces of drag and buoyancy, gravity and thrust. When viewed from below, the patterns on its body, dark vertical stripes fading toward the tail, do more than lend it the name tiger. They act as dynamic camouflage, breaking up the shark's silhouette as sunlight filters down through moving waves. Prey swimming above the drop-off cannot distinguish the predator's outline from the striped shimmer of the reef shadows below. The edge rider thrives in ambiguity. On one side of its patrol route lies the reef, home to turtles, groupers, and the occasional sickly ray. On the other, the open blue, where migrating fish schools, tired seabirds, and floating debris gather along current fronts. Each patrol can last hours, sometimes days. Satellite tracking reveals tiger sharks tracing long arcs between reef mouths, returning to the same drop-offs season after season. They're not wanderers in the random sense. Their routes are memory maps etched into muscle and brain through years of association between scent, current, and success. In these boundary zones, tiger sharks exploit what oceanographers call biological convergence. Nutrient-rich upwellings rise from the deep and collide with the plankton-heavy shallows. Small fish gather to feed on the microscopic bloom. Larger predators follow the fish, and turtles and seabirds join the frenzy. The tiger shark does not need to chase. It only needs to wait where the energy concentrates. Like a toll collector at the entrance to the reef, it taxes the traffic that flows past. When it decides to strike, the change is instant, from spectral drift to ballistic motion. The same hydrodynamic advantage that helps the shark cruise efficiently also lets it pivot with explosive precision. As it crosses the shear line, it uses a short burst of tail beat acceleration. The muscles along its body contract in a whip-crack sequence, generating power that surges through its tail and propels it forward at up to 20 miles per hour. The prey, often a green sea turtle or a reef fish, disoriented by the current's crossflow, has less than a second to react. In that moment, the tiger shark's strategy becomes clear. It has used the ocean's own architecture as camouflage, approaching not from open water or reef, but from the turbulence itself, where sound and motion blend into chaos. Few predators understand the ocean's geometry the way a tiger shark does. Its hunting efficiency relies less on pursuit and more on positioning, reading gradients, predicting movement, and exploiting contrast. To an underwater camera, the sequence looks deceptively simple. The shark veers along the current boundary, the fin angles by a fraction, and then it disappears into the darker blue. A second later, a flash of silver or a puff of sand marks the end. But in that instant lies a chain of decisions shaped by evolutionary intelligence. Sensory inputs processed through electroreceptors in the snout, lateral line vibrations along the body, and visual cues tuned to detect polarized light. Every sense the shark has converges on a single task: detecting edges. Not just edges in form or shadow, but in flow, density, and sound. Electroreception, through the ampullae of Lorenzini, plays a key role. These gel-filled pores allow the shark to sense the faint electric fields produced by muscle contractions in nearby animals. When prey enters the mixed layer of the current front, turbulence scrambles its escape cues. Its smell and vibration blend into noise, but electricity cuts through. To the shark, it is like a heartbeat glowing in fog. Once within range, the predator aligns itself with the field gradient, head cocked slightly, the pectoral fins adjusting to maintain depth. Then, a small tilt of the snout fine-tunes the trajectory. The strike is almost always from below and to the side, a tactic that maximizes surprise and minimizes the prey's defensive options. This approach also explains why tiger sharks are frequent visitors to channel mouths and passes between islands. These are natural funnels, concentrating everything from drifting logs to nesting turtles. When the tide rushes in, prey is carried through narrow gaps where the flow speed doubles, leaving them momentarily helpless against the current. The shark holds just outside the jet, where the pressure drops and energy demand is minimal, waiting for a misstep. Then, with a flick of the tail, it surges across the boundary and intercepts. Divers who have witnessed such moments describe it as a blur, a creature appearing from nowhere, hitting with surgical precision and vanishing back into blue nothingness. But there is more to the tiger shark's edge riding than hunting. It is also a strategy for energy management in vast, unpredictable oceans. These sharks travel enormous distances, from tropical reefs to temperate coasts, and even into the open Pacific gyres. To sustain such movement, they exploit every hydrodynamic advantage available. By cruising along current boundaries, they effectively draft behind moving water, reducing the cost of locomotion much like cyclists in a peloton. Satellite tag data show tiger sharks diving to different depths to catch these favorable flows, sometimes descending several hundred feet to find cooler, denser layers that act as underwater conveyor belts. Temperature plays another critical role. As ectotherms, tiger sharks rely on the surrounding water to regulate their body temperature. In warm surface layers, metabolism runs high, ideal for digestion after a meal, but costly for long travel. Deeper, colder currents slow metabolism and extend endurance. By oscillating between these layers, rising to warm up, sinking to cool down, the shark maintains an efficient thermal rhythm. Oceanographers studying their movement patterns have compared it to yo-yo diving, a behavior seen across large pelagic species that blends navigation, thermoregulation, and energy conservation into one seamless system. Every detail of the tiger shark's physiology serves this roaming life. Its liver, occupying nearly a quarter of the body cavity, is filled with low-density oil that provides buoyancy control. Its skin, covered in dermal denticles shaped like tiny hydrodynamic tiles, channels water smoothly over its surface, reducing drag. Even the slightly blunted snout contributes to stability and turbulent flow, preventing the shark from pitching as it crosses current boundaries. Nothing about its design is random. Each trait has been shaped by millions of years of evolution to turn a potential disadvantage, such as a slow cruising speed, into mastery of environment. Yet for all its mechanical precision, the tiger shark remains an ecological wildcard. It does not specialize in any one prey or habitat, but instead adapts fluidly to what the ocean offers. It scavenges whale carcasses, raids turtle nesting beaches, and even ventures into estuaries and harbors. This flexibility allows it to exploit the unpredictable, the very essence of life along edges. In a changing climate where ocean currents shift and ecosystems reorganize, few predators are better equipped to follow the new boundaries that form. To watch a tiger shark glide along a reef drop-off is to glimpse evolution's compromise between power and patience. It is not the fastest shark, nor the strongest, nor the most specialized, but it has learned the secret language of the ocean's seams. Here, where two worlds meet, it turns fluid physics into predation art. Each pass along the edge is a lesson in how nature rewards those who listen to the water, not those who fight it. And so the camera drifts backward, the reef fading beneath, the blue deepening ahead. The shark tilts slightly, catches another current line, and slides into the vast unknown. Around it, plankton flicker in the fractured light like embers on the tide. The edge moves, the predator follows, and the rhythm continues, the endless patrol of the edge rider, guardian of the boundary between worlds. At the outer edge of a reef lagoon, where waves lose their rage and curl into a slow, glassy exhale, the ocean's floor looks quiet. It appears like nothing more than a soft, rippled sheet of sand, sculpted by the push and pull of tides. But beneath that illusion of calm lies a predator that has turned the seabed itself into both camouflage and weapon. The stingray waits here, a living disk of muscle and patience, its body cloaked beneath a thin layer of sediment so perfect that not even a shadow betrays its shape. What looks like an unbroken stretch of sand is in fact a loaded spring of hydrodynamic precision. From above, a gentle shimmer hints at motion, just the faintest pulse of sand grains lifting and settling. A small goby drifts by, followed by a juvenile mullet tracing the safety of the shallows. They sense nothing. Beneath them, the stingray holds perfectly still, only the slow contraction of its spiracles, small holes behind the eyes, drawing in filtered water for breathing. It is one of nature's oldest ambush systems, stillness as camouflage, patience as predation. For as long as there have been rays, this has been their theater, the dance of still sand waiting to explode. The stingray's body design tells the story of this strategy. Flattened into a near-perfect circle, the ray's pectoral fins form broad wings that merge seamlessly into the head. This design isn't just about gliding through water, it's a structure optimized for manipulating the seabed. When the stingray settles, it flexes the margins of its fins upward, channeling sand beneath its body. Then, with a few rhythmic undulations, it exhales jets of water through its gill openings, fluidizing the sediment around it. The grains lose cohesion and slip into the microcurrents, cascading over its back until the animal disappears. What remains is a smooth, undisturbed sheet of sand, a living trap hidden in plain sight. But the stingray's true genius lies not in concealment alone. It lies in how it turns that concealment into a sudden explosive advantage. When prey wanders near, the ray's entire body becomes a piston. The muscles beneath its fins, powerful sheets of tissue layered like aircraft hydraulics, contract in a rapid sequence. This motion does two things at once. It blasts the sand upward in a fluidizing wave and collapses the surrounding water inward, creating a temporary low-pressure zone around the body. The result is what marine physicists call sediment fluidization, the transformation of solid sand into a near-liquid suspension. For the stingray, it is both cover and propulsion system. In that brief moment, the ocean floor erupts. A circular plume of sand bursts outward like a detonation muffled by water. Within the cloud's heart, the stingray launches forward, riding the collapsing fluid as if surfing on liquid air. The motion is nearly frictionless. For a fraction of a second, drag vanishes as the body slides through the liquefied layer. To a high-speed camera, the effect is astonishing. A disk of muscle flicks its wings once, twice, and suddenly a cloud blooms and collapses, with a fish vanishing in its center. The stingray has mastered the art of using the environment's instability, the chaos of moving particles, as an ally rather than an obstacle. What makes this ambush especially effective is the stingray's control over the vortices it generates. When its fins snap upward and outward, they form spinning pockets of water, circular eddies that roll over the edge of the body like smoke rings. These vortices serve two purposes. They trap suspended sand, keeping the cloud dense enough to obscure vision, and they curl inward along the stingray's body, sealing off-escape routes for prey. Fish caught within this fluid storm experience sudden sensory overload. Light diffuses, pressure shifts, and water movement scrambles their lateral line perception. In other words, they are blind, deaf, and directionless, just as the stingray lunges through the center. The ambush sequence happens in less than half a second, but it embodies a blend of physics and biology so precise it feels engineered. The stingray's disc-like body acts as both weapon and shield. The dorsal surface, smooth and slightly convex, channels water efficiently over it during the burst, while the ventral side, textured and muscular, delivers the force. The margin of the fins acts like a flexible spoiler, adjusting the direction of thrust as the animal moves. Once the prey is pinned against the sand, the stingray's mouth, located on the underside, clamps down with crushing dental plates. Unlike sharks, stingrays don't tear, they grind. Their teeth are arranged in flat, pavement-like mosaics, ideal for crushing the shells of crabs, mollusks, and small fish. To understand how this system evolved, one must look to the stingray's ancestors, the batoids, which diverged from sharks more than 150 million years ago. Over time, they traded speed for stealth, replacing the streamlined torpedo body with a flattened one suited for bottom life. The transformation was profound. The pectoral fins grew enormous and fused with the head, while the tail, once a main propulsive organ, became secondary. Many stingrays now use the tail mainly for steering, and in some species, defense. The venomous barb, a jagged serrated spine coated with mucus and venom, sits near the tail's base, ready to slash at predators or unwary intruders. This venom, rich in enzymes that cause tissue breakdown and intense pain, is not used for hunting but as a last resort. The stingray's primary weapon remains surprise. But ambush predation in stingrays is not a simple matter of hiding and lunging. It is a dynamic strategy shaped by currents, light, and even the type of sediment. In coarse sand, fluidization requires more effort. The grains are heavier and settle faster, so the stingray must flick its fins with greater amplitude. In fine silt, the cloud lingers longer, providing better cover, but risking suffocation if the ray remains buried too deeply. Some species, like the blue-spotted ribbon-tail ray, choose intermediate substrates, soft enough to conceal, firm enough to support rapid motion. Others, like the larger southern stingray, are powerful enough to operate even on compacted seabeds, creating their own micro-explosions of sediment that leave craters behind. These craters, interestingly, often become temporary feeding pits for smaller fish and invertebrates once the stingray moves on, a quiet, ecological ripple in the aftermath of violence. The stingray's sensory world enhances its ambush capabilities further. Along the leading edge of its face lies an array of electroreceptors, the ampullae of Lorenzini, the same structures found in sharks, but often more densely packed. These receptors detect the faint bioelectric fields emitted by the muscle contractions of buried or nearby prey. Even the flick of a fish's gills or the twitch of a crab claw can register. In low visibility conditions, where eyes and smell fail, electricity guides the stingray's strike. Laboratory experiments show that rays can pinpoint buried prey within centimeters, even through several centimeters of sand. Their attacks are not guesses. They are precision-guided by evolution's most sophisticated sensory technology. In the wild, the stingray's ambush often goes unnoticed by divers or predators alike. Only when viewed from the side, against the light, does the artistry of the move become visible. The sand plume expands as a symmetrical halo, the fin tip slicing through it in arcs, the central body vanishing into its own dust. Then, within the swirling chaos, a flash of motion, the fin margin rising, the disc tilting, and the prey pinned beneath. In slow motion, it looks almost graceful, like a dancer disappearing into a puff of smoke. But within that grace is raw lethality, honed by millions of years of survival on the ocean floor. Ecologically, stingrays are vital engineers. Each ambush, each feeding excavation reshapes the seabed. As they dig and stir, they oxygenate buried layers, releasing nutrients trapped beneath. These nutrients feed plankton blooms, which in turn support small fish, the very prey stingrays later hunt. In this way, they maintain the productivity of shallow marine systems, acting as catalysts for both destruction and renewal. It's a paradox of nature's design. The predator's violence sustains the prey's world. The stingray's reliance on sediment manipulation also places it in an evolutionary niche few others occupy. Unlike active chasers such as sharks or barracudas, rays depend on the physics of their environment. Their predation success rises and falls with changes in current and turbidity. During calm tides, the ambush works perfectly. During strong wave surges, the sand becomes too unstable, collapsing before the ray can strike. As a result, stingrays develop a remarkable sense of timing. They learn to hunt in short windows between tides, when the surge softens, but the current still carries enough particles to mask their motion. Researchers have noted that many ray species synchronize their feeding with lunar cycles, exploiting the slight tidal lulls that occur during half-moon phases. Evolution has turned them into not only hunters, but mathematicians of rhythm, reading the pulse of the planet's oceanic metronome. Predators that specialize in this kind of ambush face another challenge: avoiding becoming prey themselves. Larger sharks, particularly hammerheads and tigers, frequently patrol the same sandy plains. A buried stingray is well hidden, but once it moves, it risks exposure. That is why its sand burst serves a dual function, offensive and defensive. The explosion of sediment can startle a potential attacker just long enough for the ray to vanish again. By reversing its fin motion, the stingray can suck itself back under the sand in seconds, sealing the surface so perfectly that only a thin, circular imprint remains, the ghost of an ambush that might happen again minutes later. In a world where efficiency is the ultimate survival currency, the stingray's ambush technique stands as a masterpiece of energy economy. It wastes nothing, not movement, not opportunity, not breath. Its success depends on the choreography of physics and biology aligning perfectly: sand density, current velocity, body angle, fin flick. One misstep, and the prey escapes. 1 degree off in timing, and the sand gives away the trap too soon. But when it works, it is one of the most elegant predator maneuvers in the ocean, a strike that combines invisibility, disorientation, and propulsion in one unified act. As the camera pulls back, the water clears. The crater left behind slowly fills in with drifting sediment, erasing the evidence. Tiny shrimp and wrasses venture in, scavenging leftovers. The stingray is already gone, sliding to another patch of sand, preparing to vanish again. The cycle continues: concealment, patience, eruption, silence. The stingray remains the ocean's quiet tactician, the master of the sandburst ambush, proving that in nature, stillness can be as deadly as speed, and that sometimes the most fearsome predator is the one you never even see. Beneath the cold grey skin of the continental shelf, where sunlight fades to a pallid haze and only muted tones of brown and blue remain, the sea floor holds an ancient predator that moves less than almost any other creature of its size. The monkfish, also called the goosefish or angler of the deep, does not chase, sprint, or strike in the traditional sense. It waits. It waits in a stillness so absolute that silt settles across its back, barnacles attach to its skin, and small fish mistake it for a harmless patch of rock. Here in the near-freezing quiet, the monkfish has turned physics itself into a hunting strategy. Its weapon is not speed, strength, or venom, but pressure. The manipulation of water flow through anatomy evolved to exploit the ocean's most constant element. The monkfish is an ambush predator in the purest definition of the term. Its flattened body, enormous head, and almost grotesquely wide mouth dominate its form, giving it the appearance of a head with fins attached. This exaggerated shape is no accident. On the seafloor, form dictates flow. Every contour of the monkfish's body redirects the slow bottom current into controlled patterns that conceal its presence and funnels scent and motion toward its senses. The skin is mottled with uneven patches of brown and beige that mirror the sediment and crushed shells beneath it. Around the edges of its fins, fleshy lobes flutter in the current, perfectly mimicking strands of seaweed. The disguise is so complete that even small crustaceans crawl across its head without realizing they tread on a predator capable of swallowing them whole in a fraction of a second. But the monkfish's true magic begins not with sight or stealth. It begins with a single appendage on its head. From the center of its forehead extends a modified dorsal spine tipped with a fleshy lure called the esker. This small filament, no longer than a finger, wriggles and trembles with minute precision. The monkfish flexes the base muscle of the spine in rhythmic pulses, creating a gentle motion that perfectly imitates the drift of a small worm or shrimp. Yet what makes this lure extraordinary is not merely the movement, but the microcurrents it generates. The esker disturbs the surrounding water just enough to create tiny eddies, subtle spirals that nearby fish detect with their lateral lines. To them, these eddies feel like the wake of a small creature moving through cover, something alive but safe to approach. It is a trick written in fluid mechanics, not illusion. Around the lure, the monkfish's mouth gapes open slightly, a cavernous hollow lined with backward-pointing teeth. At rest, it looks like nothing more than a crevice in the seabed. Inside, however, the geometry of the jaw and oral cavity forms a pressure chamber. When the monkfish senses movement near the lure, whether through vibrations, changes in light, or the minute electric field of an approaching fish, its entire head transforms into a pump. In less than 1/20th of a second, the monkfish expands its buccal cavity and flares its gill covers outward. This sudden expansion causes an immediate drop in pressure inside the mouth. Water, following the laws of fluid dynamics, rushes in to equalize the difference, carrying with it everything in its path. The result is a vacuum-driven ambush so fast that the prey does not have time to react. The fish or shrimp feels a tug, a sudden shift in current, and before its muscles even register danger, it has been sucked into the monkfish's mouth. The acceleration of water during this strike can exceed several body lengths per second, not because the predator moves quickly, but because the surrounding fluid does. The monkfish weaponizes the very medium it lives in, turning water into a conveyor of death. The beauty of this system lies in its efficiency. Most predators expend tremendous energy chasing down prey or maintaining speed over long distances. The monkfish, however, spends nearly all its time immobile. Its metabolic rate is astonishingly low, adapted for cold, oxygen-poor waters. By anchoring itself to the seafloor and letting the currents bring food within range, it conserves energy to an extreme degree. The strike itself, that sudden inhalation of power, is powered entirely by stored elastic energy in the jaw and gill muscles. Once released, it's over in the blink of an eye, and the predator returns instantly to stillness. Hydrodynamic modeling of monkfish strikes reveals that the suction field extends far beyond what its mouth size would suggest. The shape of the jaw opening, slightly elliptical and slanted downward, acts like a directional funnel. This not only increases the capture radius, but also minimizes sediment intake, a critical adaptation for an animal that feeds directly on the bottom. By angling its mouth and body just so, the monkfish ensures that its vacuum pulls from the water above the sand layer, drawing prey cleanly into its mouth without choking on debris. The lower jaw, flexible and heavily muscled, scoops downward slightly at the last moment, creating a secondary upward flow that prevents escape once the water rushes in. The prey rarely even touches the outer lip before being engulfed. Once inside, the mouth closes with a clap of force strong enough to crush small crustaceans. The inward-pointing teeth act as barbs, ensuring that nothing leaves once it has entered. From there, the monkfish's stomach, capable of expanding to several times its resting volume, accommodates meals that can be nearly half the predator's own body size. There have been recorded instances of monkfish swallowing seabirds, eels, and even small sharks whole. Beyond its feeding mechanics, the monkfish's body tells a story of evolutionary compromise and specialization. Its fins, positioned like stubby arms, are not for swimming, but for crawling. Each pectoral fin can rotate at its base, allowing the fish to walk along the bottom, repositioning itself silently without disturbing sediment. Its dorsal surface is rough and covered with sensory pits that detect changes in pressure and current direction, a network of hydrodynamic receptors that give it an almost three-dimensional awareness of its surroundings. This allows it to anticipate the movement of prey before visual contact, effectively feeling the world around it in the language of flow. In evolutionary terms, monkfish belong to the order Lophiiformes, a diverse lineage of anglerfish that includes both shallow water and deep-sea species. While their relatives in the abyss evolved bioluminescent lures and elongated jaws, the monkfish adapted to coastal shelves, refining suction mechanics for dense, cold, nutrient-rich habitats. Its success in these marginal environments has made it one of the top predators of the benthic food web. Wherever sand meets rock and current meets stillness, monkfish thrive. Ecologically, the monkfish occupies a pivotal role. By preying on fish that dwell near the bottom, flatfish, gobies, sand eels, and small cod, it regulates population balance across the benthic ecosystem. Its feeding also stirs sediment layers, resuspending organic matter that feeds invertebrates and detritivores. Even the discarded remains of its meals attract scavengers, creating small hotspots of activity on the otherwise barren seafloor. In this way, the predator's feeding becomes an act of recycling, linking energy flow between different trophic levels of the marine system. Yet perhaps the most striking aspect of the monkfish's hunting design is how it mirrors natural principles found across scales, from storm fronts to galaxies. Pressure differentials drive motion everywhere in nature, and the monkfish has evolved to embody that law at the biological level. It does not fight the physics of its environment, but bends it to its advantage. The ocean, in return, rewards this patience with sustenance. To witness the moment of strike in ultra-slow footage is to watch the laws of motion play out with chilling precision. The lure flickers. A small fish glides closer. The monkfish remains immobile, eyes fixed forward, its skin indistinguishable from the sand. Then a ripple crosses its back, the faint contraction of hidden muscles. The mouth opens wider than seems possible, the head balloons outward, and the surrounding water convulses inward. For an instant, the prey's body bends unnaturally as the pressure wave drags it forward. There is no pursuit, no chase, no visible violence. Only a silent implosion, followed by stillness once more. The camera drifts closer, showing the aftermath. A few grains of sand drift upward, settling across the predator's snout as it resumes its vigil. The lure twitches again and the entire cycle resets: motion, deception, vacuum, silence. It is an art form built on nothing but timing and physics. An elegant demonstration that predation in nature is not always about speed or aggression. Sometimes it is about understanding how the world moves and placing oneself perfectly within that motion. In the dark expanse of the continental shelf, where pressure crushes lungs and silence reigns, the monkfish is both sculptor and subject of the sea's unseen forces. It shapes flow, commands stillness, and transforms water into a weapon. For those who think of predators as creatures of pursuit, the monkfish offers a humbling correction. Sometimes the deadliest hunter is the one that never moves, the vacuum trap waiting patiently on the seafloor, turning the very breath of the ocean into its kill shot. In the shallows, where sunlight fractures into 1,000 moving shards, the cuttlefish drifts like a dream half remembered. It seems almost unreal, a shape that keeps changing, colors flickering across its skin like passing thoughts. Yet beneath that hypnotic shimmer lies one of the most sophisticated hydrodynamic hunters in the ocean. Unlike predators that rely on brute force or speed, the cuttlefish has evolved to master control of motion, of water, of perception itself. Its domain is not the open chase, but the silent approach, the art of arriving unseen until the instant before the strike. To watch a cuttlefish hunt is to witness choreography more than pursuit. The scene opens in a field of seagrass or a coral alley, the current slow and the water thick with suspended particles. Small shrimp hover among the blades, their antennae sweeping for vibrations. They can sense even the smallest pressure waves through the lateral line, a sensory array that reads disturbances in the water's movement. For most predators, this sense is a near impenetrable defense barrier. Any thrust, any ripple, and the prey bolts. but the cuttlefish has learned to manipulate the medium itself. It understands, through instinct refined over millions of years, how to move in water without revealing its presence. The cuttlefish's mantle, the muscular sac behind its head, is its engine. Within, twin siphons control the flow of water expelled for propulsion. Unlike the constant thrust of a squid's jet or the undulating power of a fish's tail, the cuttlefish's jet is measured and intermittent, controlled down to fractions of a second. When it pulses, it releases a precisely calibrated burst of water that moves not just the body but the fluid around it. The result is a sliding motion, smooth and laminar, almost frictionless. Each pulse fades just before turbulence can form, a timing perfected through generations of evolutionary tuning. In engineering terms, the cuttlefish operates at the threshold of flow separation, hovering at the line between motion and stillness. This delicate balance allows the animal to exploit what physicists call a prey's hydrodynamic blind zone, the narrow cone of still water directly behind its own wake, where pressure gradients cancel out and lateral line sensors go silent. To enter that zone, the cuttlefish must align itself perfectly with the direction of water flow and match its own thrust to the prey's drift. A single miscalculation and the vortex trail gives it away. But the cuttlefish doesn't miscalculate. Its eyes, among the most advanced in the animal kingdom, perceive polarization and contrast far beyond human vision, reading not just light, but the movement of particles suspended in the current. Through these cues, it can see invisible rivers within the sea, the invisible trails left by each creature's motion. When it begins its approach, the cuttlefish engages in what biologists call a fin stall crawl. Its wide, ribbon-like fins undulate in slow ripples along the mantle's edge, generating small, opposing vortices that neutralize drag and maintain position. This is station-keeping at a level of mastery few marine animals can match. The fins act as fine-tuned control surfaces, parts of them pushing forward, others pulling back, allowing for movement so stable that even a feather drifting nearby remains undisturbed. The cuttlefish can hover motionless for minutes, its skin shifting to match every flicker of light and every grain of sand below, before gliding forward in a near-perfect state of hydrodynamic invisibility. Camouflage, of course, is its trademark, but the popular imagination often overlooks how inseparable it is from movement. The cuttlefish's chromatophores and iridophores don't merely change color, they adjust pattern speed and direction to synchronize with background motion. When sunlight refracts through surface waves, the animal's skin pulses with a similar rhythm, its light bands chasing each other in waves that match the flicker of their efflore. Even subtle roll angles and fin beats are matched to these patterns, so the entire animal becomes a moving echo of the environment. The goal is not simply to look like the surroundings, but to move like them. But the true revelation comes in the final seconds of the hunt. As the cuttlefish nears striking range, roughly the length of its body, it performs an act of hydrodynamic sleight of hand. It stops jetting. The siphons close, the fins cease undulating, and the body glides forward on inertia alone. This is the stall. For a brief instant, there is zero self-generated noise, zero turbulence. In that silence, it becomes a ghost in water, a floating pressure shadow. The prey's lateral line reads only the background flow, unaware that a predator now occupies its own blind spot. Then the tentacles fire. Two specialized feeding arms, coiled beneath the head like loaded springs, shoot forward at blinding speed. In less than a 20th of a second, they extend to their full length, guided by suction cup-lined clubs that grab and retract before the prey can react. High-speed footage reveals the elegance of the mechanism. A split-second jet of fluid through the arm cavities stiffens them into lances, while elastic recoil snaps them back. The strike is not just fast, it is coordinated to the animal's hydrodynamic rhythm. The tentacles move in the same direction as the water flow created by the final jet pulse, minimizing drag and preventing telltale ripples that could alert other prey. It is a seamless blending of physiology and physics, an ambush so refined it feels more like engineering than biology. What happens next is just as fascinating. Once the prey is caught, the cuttlefish doesn't flee or thrash. It simply reverses its jet, using a backward thrust to counter the momentum of the strike. In doing so, it cancels the wave pattern that would otherwise ripple outward. This self-cancelling motion prevents scavengers and competitors from detecting the kill. Even in predation, the cuttlefish remains invisible, managing the acoustic and pressure signatures of its own movements like a submarine trained for stealth warfare. Underneath this mastery lies a dense network of sensory control. Along the body, a system of mechanoreceptors, similar in function to the lateral line in fish, detects minute changes in flow and pressure. Combined with its neural precision, the cuttlefish adjusts fin amplitude, jet frequency, and even skin tension in real time. Its brain, proportionally large for an invertebrate, integrates visual, tactile, and hydrodynamic data in a feedback loop that allows split-second corrections. It is not instinct alone that guides its motion, but computation, a living algorithm tuned to the ocean's turbulence spectrum. From an evolutionary standpoint, this control system reflects the cuttlefish's dual challenge: to hunt and to avoid being hunted. Many of its predators, groupers, sharks, dolphins, rely on their own lateral lines and sonar to detect motion. The cuttlefish's ability to erase its hydrodynamic footprint is not only offensive, but defensive. By understanding how water transmits sound and vibration, it exploits the sensory limitations of both predator and prey. In this way, it becomes a master of absence, surviving by not existing in the perceptual world of others until the moment of action. The implications of this go beyond simple predation. The cuttlefish's maneuvering systems have inspired research in underwater robotics, where scientists study how its low-turbulence jets and flexible fins could lead to more efficient propulsion in variable currents. Engineers have replicated aspects of its fin undulations in soft robotic designs that can maintain stability without rigid control surfaces. In the cuttlefish, nature has achieved something that modern science still struggles to perfect: silent, precise motion in a fluid medium that resists silence and precision. Behaviorally, these skills also serve social and reproductive roles. During mating displays, males use the same control over flow and patterning to signal dominance or submission. A male courting a female will often shift half his body into bright zebra stripes, a threat pattern aimed at rivals, while the other half remains in camouflage facing the female. To maintain this split display, he must control not only pigment cells, but also the fine rippling of skin texture, called papillae, that alters how light and shadow play across his form. The hydrodynamic stillness he maintains during this display ensures that his message reaches visual receptors, not the lateral lines of lurking predators. Even courtship is conducted in stealth mode. And yet, for all its precision, the cuttlefish remains fragile in the larger scheme of evolution. Its lifespan rarely exceeds 2 years. Each generation must relearn the same hydrodynamic ballet from instinct alone. There is no parental teaching, no cultural transmission. Its perfection exists in the moment, coded into muscle memory and neural wiring, performed once, then gone. This impermanence lends its mastery a strange beauty, like a dance written on water that vanishes the instant it's completed. In the end, what defines the cuttlefish is control, not domination, not strength, but the ability to shape perception through physics. It hunts not by breaking the water, but by joining it. Every jet, every stall, every ripple of fin and shift of skin is part of a single philosophy: move with the flow, not against it. When it strikes, it is not an intruder, but an inevitability. The ocean's own motion, momentarily condensed into flesh and purpose. As the camera follows it into the fading light, the cuttlefish drifts once more into invisibility. The sand below still ripples from its passing, but the animal itself is gone, folded back into the shimmering mirage of current and sunbeam. Somewhere ahead, another prey hovers, oblivious to the approaching silence. The ocean waits, still and alive, until the next pulse of the jet, and then once again the predator vanishes into shadow. In the deep blue between reef and open sea, where the water turns from turquoise clarity to an endless cobalt haze, the manta ray moves like a living current. Its wingspan stretches wider than a human car is long, yet it glides with the silence and precision of a drifting cloud. Around it, the plankton-rich sea is in perpetual motion, billions of microscopic lives suspended in a slow, invisible storm. For most creatures, this drifting abundance is chaos, unpredictable, dilute, and difficult to capture. But for the manta ray, it is a system waiting to be organized. Through anatomy, behavior, and physics, the manta has turned the turbulence of the ocean into an assembly line of food. It is not just a filter feeder, it is a living flow machine, a creature that harvests motion itself. Seen from below, a feeding manta looks like a slow-turning aircraft in perpetual flight. Its enormous pectoral fins undulate with a rhythm that seems effortless, but each movement is a masterclass in hydrodynamic control. Unlike ordinary swimmers, mantas do not simply push water backward, they shape it. Along the leading edge of the fins, the slight curve and flexible tips generate lift much like an airplane wing, not to rise through air, but to manipulate density gradients in water. Each undulation generates small vortices that roll off the fin edges, forming coherent flow structures that pull water toward the mouth. The result is not a random sweep through plankton, but a carefully engineered capture zone, a region of organized flow converging toward the manta's open mouth. At the front of this machine lie its most remarkable tools, the cephalic fins. These are the twin lobes, like unfurling horns that extend forward from either side of the mouth. When feeding begins, the mantas roll these fins forward and down, curling them into spirals that guide water inward. They are not simply scoops, but dynamic flow shapers, capable of adjusting the intake angle and curvature to fine-tune how plankton-rich water enters the mouth. Each subtle twist alters the way pressure builds along the front edge of the animal's head, directing currents with surgical precision. The process is akin to a turbine adjusting its blades in real time, optimizing efficiency based on the density and direction of incoming flow. Once inside, the manta's oral cavity becomes a filtration chamber unlike any other in the ocean. Traditional filter feeders, such as whale sharks or basking sharks, rely on passive sieving. Water flows through gill rakers, and particles are caught on mesh-like structures. But mantas employ something more advanced, a mechanism known as ricochet filtration. Here, water doesn't simply pass through a screen. Instead, it flows around rows of intricate filter lobes that redirect and accelerate the current in patterns that fling particles away from escape routes. In doing so, the manta collects plankton without clogging its filters, a self-cleaning design so efficient that engineers study it for inspiration in industrial fluid systems. When plankton concentrations rise to their seasonal peak, especially in upwelling zones or near reef passes, mantas gather in numbers, transforming the sea into an aerial ballet of feeding loops. This behavior, called cyclone feeding, is one of the most striking examples of collective fluid dynamics in nature. Dozens of mantas spiral together in coordinated columns, each individual maintaining a precise position relative to those above and below. The geometry is far from random. By flying in a vertical circle, the mantas create a continuous vortex ring where the downward stroke of one feeds the upward draw of the next. This circular flow concentrates plankton toward the column's core, amplifying feeding efficiency while minimizing wasted energy. At the heart of this phenomenon lies an elegant physical truth. Vortices in water can act like conveyor belts. When a body moves in a circle, it generates a rotating torus of flow, a donut-shaped ring of spinning water. If timed correctly, multiple rings can link together, reinforcing one another to form a stable vortex column. In cyclone feeding, each manta positions itself at the optimal distance, not too close to disrupt the neighbor's wake, but near enough to harvest the energy of the shared current. By aligning their wing beats with this collective rhythm, they reduce the drag that any one animal would face alone. The system functions like a factory line in motion, each manta part of a synchronized machine, each movement both personal and communal. From the outside, it is mesmerizing. The spiral column rises and falls in slow, deliberate cycles, a living whirlpool of giants. The sunlight penetrates through the water, flickering across their backs like molten metal. Plankton swirls visibly in the center, drawn by invisible physics into an edible funnel. Each animal glides with mathematical grace, wings angled, cephalic fins curled, mouth agape, while the surrounding sea churns in response. The feeding frenzy looks chaotic from afar, but high-resolution tracking shows order. Every manta maintains a steady phase offset, ensuring no collisions and no wasted thrust. The collective flow they generate can double the plankton density within their feeding ring, turning the surrounding ocean from a thin soup into a dense, pulsing concentrate. But the manta's genius extends beyond cooperative feeding. Even when alone, it reads the sea like a map of invisible rivers. Water is never static. It moves in filaments, shears and gradients shaped by wind, tides, and temperature. These features, though unseen, leave detectable fingerprints. Differences in turbidity, light scattering, and suspended particle density. Mantas navigate through these patterns using both vision and an array of sensitive electroreceptors embedded along the head and body. These sensors detect minute voltage changes caused by water movement and living prey, allowing the manta to identify the most productive feeding lanes even in dim or murky water. In essence, it senses the shape of motion itself. Physiologically, the manta ray's adaptations for sustained gliding and flow control are extraordinary. Its muscle fibers are dominated by slow-twitch aerobic cells that resist fatigue, allowing hours of continuous flight-like swimming. The cartilage of its skeleton is reinforced by layers of mineralized collagen, giving flexibility without sacrificing structural integrity, ideal for wings that must flex with the currents rather than fight them. Even its skin is an engineering marvel, covered in microscopic ridges that reduce drag by creating a thin boundary layer of trapped water, similar to the texture of a shark's dermal denticles, but optimized for laminar flow rather than speed. Despite their size and grace, mantas live in a precarious balance between abundance and vulnerability. Their entire existence depends on the consistency of plankton blooms and the stability of ocean currents. Climate change threatens both. Alterations in sea temperature shift the location and timing of plankton upwellings, leaving mantas to search longer distances for food. Satellite-tagged individuals have been recorded traveling hundreds of miles between feeding zones, tracing oceanographic features like eddies and thermoclines as if following invisible highways. The cost of such migrations is immense. Even the efficiency of their flow mastery has limits when the factory line moves beyond reach. Reproduction adds another layer of complexity to their lives. Mantas give birth to live young after nearly a year of gestation, producing only a single pup at a time. That slow reproductive rate, combined with increasing fishing pressure, has made them especially susceptible to population decline. Their gill rakers, once the key to survival, have become their downfall, harvested for use in unproven medicinal products. Ironically, the very structure that demonstrates nature's most elegant fluid mechanics has been turned into a commodity of superstition. Conservation programs now track their migration routes, protect key feeding and breeding sites, and work to curb international trade, but recovery is slow. The ocean's flow machine, once abundant, is now a rare and delicate wonder. Still, when conditions align, the plankton thick, the tides steady, the moon full, the spectacle returns. From the shadows of deep channels, mantas rise by the dozens, turning the water into a spinning cathedral of movement. Each animal plays its part in the grand mechanical ballet, refining the currents into ordered motion. The scene is not just beautiful, it is instructive. It reveals how evolution finds order in chaos, how life can build machines without metal or code, machines that run on biology, cooperation, and the laws of fluid physics. As the camera pans outward, the spiral dissolves. The mantas begin to drift apart, their feeding complete. The vortex unwinds slowly, releasing its plankton back to the sea. One by one, the rays glide into the open blue, their silhouettes fading into the haze like departing ghosts of motion. The ocean resumes its usual disorder, but for a brief window, its energy was shaped, refined by wings that understood it better than any wind tunnel or human engineer ever could. The manta ray, the living flow machine, leaves behind nothing but calm water and the faint impression that the sea itself just took a breath. At first glance, the lagoon looks harmless, a sunlit mosaic of shifting blues and silvers, its surface rippling with the faintest wind. But beneath that glittering calm, a hunter glides. Long, fluid, and impossibly graceful, the sea snake moves just under the meniscus, weaving between light and shadow as if it were part of the reflection itself. Few animals embody the marriage of air and sea so completely. Neither fully terrestrial nor entirely marine, the sea snake has learned to exploit the very skin of the ocean, the surface film that divides water from air, as both its camouflage and its hunting ground. Seen from above, it nearly disappears. The snake's body is banded in pale and dark scales that mirror the flickering chaos of refracted sunlight. To fish below, the surface appears as a dancing mirror, a barrier of brightness through which nothing distinct can be discerned. The sea snake knows this. Its entire approach is designed around the physics of concealment, how light scatters, how ripples distort perception, and how water transmits vibration. By swimming just a few centimeters beneath the surface, it places itself within what marine physicists call the Snell window, a circular portal of refracted light through which creatures below perceive the world above. Here, light is fractured and polarized, and motion becomes a shimmer, not a shape. The snake has evolved not to break that illusion. The air-breathing lung that anchors its existence, the single, elongated sac running nearly the full length of its body, allows it to stay submerged for extraordinary stretches, sometimes half an hour or more. The lung is not merely for oxygen exchange. It doubles as a buoyancy control system, adjusting the snake's depth with exquisite precision. By releasing or retaining air, the sea snake can hover at a fixed depth just beneath the surface film without a single stroke. In that stillness, it becomes one with the water's skin, motionless, invisible, and waiting. When it does move, the motion is a whisper. The serpentine body undulates in horizontal waves, each coil transferring energy efficiently from head to tail. Unlike eels or fish, which generate large wake patterns, the sea snake's stroke amplitude is subtle, designed to minimize turbulence. The smaller the disturbance, the less likely the prey's lateral line will sense it. Laboratory flow visualizations confirm that the snake's undulations produce laminar ribbons of flow, smooth, continuous sheets of displaced water rather than noisy eddies. It is a perfect adaptation for a predator that hunts in the ocean's most acoustically sensitive zone, the upper meter, where sound travels far and fast, and even the faintest ripple can betray an approach. As the tide rises, the snake's hunting grounds expand. It glides into mangrove creeks, estuarine channels, and flooded routes, places where fresh and salt water meet in slow collision. These narrow passages become natural funnels for life. Schools of mullet, juvenile snappers, and gobies follow the current inward, seeking plankton and protection, unaware that the flow is guiding them straight into an ambush corridor. The snake positions itself along a bend or tidal constriction, where hydrodynamic pressure forces small fish against the outer wall. Every few seconds it lifts its head toward the surface, nostrils breaking through like the tip of a periscope, drawing in a breath so quick it barely disturbs the film. To a casual observer, it looks like nothing more than a leaf stem brushing the surface. That breath is more than respiration. It is rhythm. Sea snakes live by an oxygen clock, one that dictates both their pace and their patience. Too much activity and the clock runs down too fast, too little and prey escapes. Evolution has honed this balance to near perfection. Their blood is extraordinarily efficient at carrying oxygen, and a dense network of capillaries extends through the skin, enabling cutaneous respiration that can supply nearly a quarter of their oxygen needs. Even the trachea acts as a secondary lung, exchanging gases along its entire length. In practice, this means the snake can turn a breath stop, a vulnerability for most animals, into part of its hunting tactic. Here in the tidal creek, physics conspires in its favor. Every gust of wind, every wavelet from an upstream bend scatters sunlight into a broken mosaic of flashes. To fish, this glare is both shield and prison. Their polarized vision, so useful for reading patterns in calm water, becomes useless in chop. The surface no longer reflects an image. It becomes a field of brightness without meaning. The snake, watching from below, sees opportunity. Its eyes, positioned high on the head, are adapted for upward vision. They can detect silhouettes and contrast across the glitter field that blinds its prey. When a small mullet ventures too near the surface, the snake launches upward in a near-vertical coil, jaws unhinging in an instant. The strike is a study in controlled violence. Unlike its terrestrial relatives, the sea snake's fangs are short and fixed, not hinged. But what they lack in size, they make up for in potency. The venom, among the most toxic of any snake, acts quickly, immobilizing small prey almost instantly. The bite itself occurs in fractions of a second, the snake's mouth opening wide enough to engulf half the fish's head before snapping shut. Once captured, the prey is swallowed whole, head first, the fins folding smoothly backward as it slides down the muscular throat. The snake resumes its stillness almost immediately, the disturbance already blending into the shimmer above. In open coastal waters, where the sun burns brighter and the surface ripples endlessly, sea snakes adapt their tactics further. Instead of waiting near structure, they use the chaos itself as cover. Each wavelet acts like a shifting mirror, reflecting light in constantly changing directions. The snake positions itself beneath these moving reflections, synchronizing its ascent with the oscillation of the surface. To an observer from below, the predator's approach looks like just another patch of moving light. The prey's senses, overwhelmed by the constant flicker, fail to distinguish danger from harmless brightness until the shadow resolves too late. Even the body's shape plays a role in this deception. The cross-section of a sea snake is flattened laterally, forming a keel-like edge that stabilizes movement near the surface. This design also refracts light differently than round-bodied fish, breaking up its visual outline when viewed through disturbed water. Combined with a sleek scale microtexture that reduces drag and prevents bubble formation, it allows the snake to glide so quietly that even sensitive crustaceans, normally the first to react, remain motionless until the strike. Hydrodynamically, the snake's hunting technique is as much about environment as anatomy. The tidal creeks it patrols are shaped by centuries of flow erosion, forming sinuous channels where current accelerates along outer bends and slackens in inner pools. Fish instinctively shelter in these slower zones to conserve energy. The sea snake, understanding this through generations of instinct, positions itself just downstream of these eddies. When the tide surges, the fish must swim into the current to maintain position. The snake waits with its body angled against the flow, mouth slightly open, ready to intercept any that drift within reach. It is a technique of minimal movement and maximal efficiency, an ambush refined to the pulse of the tides themselves. The relationship between air and water defines every aspect of the sea snake's life. Unlike fish, it cannot rely on gills. Unlike land snakes, it cannot escape the sea's demands. Each breath must be earned, each ascent timed. To manage this dual existence, the snake has evolved an extraordinary respiratory rhythm. As it surfaces, it exhales before inhaling, clearing stale air while minimizing bubble release. This action also reduces sound, ensuring that even the act of breathing doesn't betray its position to prey or predators. It is a small, elegant detail in an animal built from evolutionary compromise, every weakness reshaped into advantage. Yet the surface, while providing both air and camouflage, is also the sea snake's most dangerous zone. Raptors like sea eagles patrol above, and predatory fish such as groupers and trevallies lurk below, waiting for a mistake. The snake's answer is mobility. It rarely lingers in one area for long. As tides turn, it drifts with them, often covering kilometers of coastline in a single day. Some species even venture far offshore, riding ocean currents between islands, their bodies coiled in resting loops on the swell. The lung, acting as a buoyant chamber, allows them to rest almost motionless in rolling waves, the head occasionally breaking through to sip air. Despite their graceful movements, sea snakes are not without clumsiness on land. Those few that return to beaches or reefs to lay eggs move awkwardly, reminding us that their evolution toward marine life is not yet complete. But underwater in their element, they are peerless, predators shaped by the interplay of light, water, and breath. Their entire hunting system is a conversation with physics: how to hide beneath reflection, how to move without leaving a trace, how to turn the act of breathing into a weaponized pause. As the camera rises with one of them toward the surface, the world inverts. The snake's body is mirrored perfectly against the underbelly of the waves, scales shimmering in silver and black. A thin film of light separates air from water, the border between two worlds it must constantly cross. It breaks through silently, nostrils flaring for a heartbeat, then vanishes again, leaving only a ripple that merges with countless others. The lagoon returns to stillness, the sun glittering across the water like nothing ever happened. The sea snake has no need to dominate its realm. It survives by understanding it, by reading the ocean's textures, using optics and flow as both shield and snare. In a place where visibility is betrayal, it thrives in transparency, turning the mirror of the sea itself into a hunting blind. Beneath every shimmer on the water's surface, beneath every glint of light, the possibility remains that a serpent waits, coiled beneath the sky, breathing between worlds. The river mouth is a place of collision, a zone where two great worlds meet and neither wins. Here, the fresh pulse of the inland water presses outward, while the ocean's tides push relentlessly in. Twice each day, the balance flips. The water changes color, direction, even temperature, as the salt front advances and retreats through the mangroves. It is a place of chaos, currents spiraling against each other, sediment clouds boiling, mullet flashing silver in confusion. And waiting in this liquid frontier, perfectly still and perfectly timed, is the saltwater crocodile, the largest reptile on Earth and perhaps its most accomplished opportunist. It does not fight the current, it becomes part of it. The crocodile knows the river's rhythm better than any tide gauge. Its hunting success depends not on speed or surprise alone, but on an intimate understanding of water itself, how pressure builds, how flow bends, and how sound travels through the dense, shifting medium. The incoming tide is its accomplice, and the tide bore, that steep, surging wall of water that races upstream when the sea floods against a narrowing river, is its delivery system. To the crocodile, the bore is not an obstacle, it is a moving trap. As the first signs of the bore form offshore, the crocodile lies half submerged along the mangrove edge, body motionless, eyes and nostrils just above the surface. Around it, the river seems calm, but beneath the skin of the water, subtle pressure changes announce what is coming. The crocodile feels them before it sees them. Tiny sensory organs, called integumentary sense organs, stud its face and jaws, each one capable of detecting the faintest vibration or shift in water pressure. These sensors allow it to read the river like braille, the pulse of an approaching school of fish, the displacement of a swimming bird, the rising hum of the bore front as it moves inland. When the surge arrives, it is not a wave as much as a moving wall. Water rises abruptly, rolling forward with a deep, thunderous sound that reverberates through the mangrove roots. The crocodile does not resist. Instead, it angles its body slightly, a maneuver known as yaw steering, allowing the flow to slide along its flanks. The wide, muscular tail provides fine-tuned control, acting like a rudder to maintain position within the boundary layer where current speed is slower. Here, drag is minimal, and the crocodile can travel vast distances without a single stroke of its limbs. Its body, armored and hydrodynamic, becomes a natural glider riding the surge. This technique of tide surfing is more than energy-saving behavior. It is a form of passive hunting. The crocodile knows that the boar will push stunned or disoriented prey ahead of it. Fish, crustaceans, and even small mammals caught too close to the edge of the flow are swept along, struggling to regain balance. The predator's job is simply to be in the right place when the current delivers them. It does this with precision learned through experience. Juvenile crocodiles experiment with positions near eddies and river bends, but adults, some over 5 meters long and weighing nearly a ton, occupy prime ambush zones, narrow channels where the bore compresses, or the mouths of side creeks where turbulence peaks. The mechanics of this ambush are as much physics as biology. As the tide bore races past, it generates a zone of reduced pressure immediately behind the front. The crocodile exploits this by sliding laterally into the void, using the difference in flow speed to drift silently across the current. Its eyes remain above the surface, protected by a nictitating membrane that allows vision underwater, while its body aligns perfectly with the flow. Every muscle is coiled but relaxed, minimizing wake signature. Even its lungs play a role. By shifting air between them, the crocodile adjusts buoyancy and roll angle, fine-tuning its posture without visible motion. It becomes a neutral observer, a shadow on the water's edge. Then comes the strike. When the prey drifts within range, a mullet caught in cross-current, a piglet washed from the riverbank, or a seabird diving at the wrong moment, the transition from stillness to violence is instantaneous. The crocodile lunges sideways, not forward, in what biologists call a cross-current snap. The motion seems counterintuitive but is biomechanically perfect. By attacking across the flow rather than against it, the crocodile harnesses the water's momentum. Its tail sweeps in a rapid S-shaped burst, generating thrust that merges with the bore's energy rather than opposing it. In that instant, hydrodynamics does half the work. The jaws, lined with conical teeth designed to grip rather than cut, clamp shut with one of the most powerful bite forces in the animal kingdom. There is no escape. The aftermath is eerily calm. The crocodile retreats into an eddy, a circular pocket of slower water just behind a submerged log or root tangle, and waits for the turbulence to pass. These eddy parks serve as both rest zones and feeding stations. Here the predator can consume its catch in relative stillness while remaining hidden from others. Because saltwater crocodiles are ambush hunters that rely on surprise rather than endurance, recovery between strikes is crucial. Each attack drains oxygen reserves, and the animal must resurface to breathe. But it does so strategically, choosing moments when the bore's aftermath creates enough surface disturbance to mask the sound and ripple of exhalation. The crocodile's mastery of the tide extends beyond ambush mechanics. It also uses these tidal surges to travel enormous distances with minimal energy. Individuals tagged with satellite transmitters have been recorded crossing entire coastal deltas, letting flood tides carry them inland and ebbing currents return them to the sea. This behavior explains their vast distribution, from river mouths in northern Australia to estuaries of Southeast Asia and even offshore coral atolls hundreds of kilometers apart. By surfing the rhythms of the ocean, they effectively erase the boundaries between river and sea. Their physiology supports this amphibious strategy. The saltwater crocodile's salt glands, located in the tongue, excrete excess sodium, allowing it to drink seawater when necessary. Its nostrils seal with muscular valves during dives, and its heart can shunt blood selectively, prioritizing oxygen delivery to vital organs while the rest of the body enters a quasi-resting state. Combined with the ability to slow its heart rate to just 2 beats per minute underwater, it can remain submerged for over an hour if undisturbed. Such adaptations make it a creature perfectly sculpted for the fluctuating world of tidal margins, a reptilian engineer in an environment governed by hydrology and physics as much as by biology. When seen from above, a tide bore can look chaotic, a sheet of brown water tearing upstream, scattering foam and driftwood. Yet within that chaos, the crocodile reads patterns. It knows where turbulence will form, where prey will stall, and where pressure fronts will break into calmer zones. Observations from drone footage show that large males often patrol the same route repeatedly, using consistent landmarks such as mangrove roots, sandbars, and even human docks as reference points. These are not random wanderers. They are navigators of dynamic terrain, returning again and again to ambush corridors that deliver predictable rewards. For smaller crocodiles, the boar presents both opportunity and danger. Juveniles often hunt the margins, targeting shrimp or small fish that scatter from the larger predator's strikes. But they must remain alert. The same surge that carries food can also carry a rival. Cannibalism is not uncommon among saltwater crocodiles, and the confusion of the tide offers the perfect cover for sudden disappearances. The ecosystem here is a hierarchy of patience. The strong dominate the best positions, while the weak adapt or are consumed. The tide itself is indifferent. Twice a day it floods and recedes, carving channels, rearranging sediment and erasing tracks. Yet to the crocodile, these oscillations are as reliable as the rising sun. Evolution has taught it to see opportunity in repetition, to turn inevitability into advantage. Its hunting success depends not just on strength or stealth, but on timing, understanding when the water will rise, where it will turn, and how it will deliver its next meal. As the camera follows one male through the final minutes of the flood, the mangroves shimmer in the late light. The boar has passed, leaving the river swollen and brown, its surface still trembling from residual energy. The crocodile drifts in the shallows, only the top of its back visible, the skin glistening like wet bark. Small fish dart around its tail, unaware that the predator is still watching, still calculating. In a few hours, the tide will reverse and the cycle will begin again. In these estuarine borderlands, the saltwater crocodile reigns not through dominance of strength alone, but through mastery of motion. It is an animal that has learned to let the world do the work, to turn water into weapon, current into camouflage, and tide into ally. Each surge that sweeps the river mouth is both a challenge and a feast. And as long as the ocean breathes in and out through these channels, the crocodile will be there, surfing the rhythm of the earth itself, patient, ancient, and utterly in command of the moving wall.